I will start with saying thank you, because usually I'm not introduced in my talks when they are in person, so that was refreshing. And I want to tell you guys that I'm using Ubuntu, and sometimes using Linux is not a walk in the park. So today I had technical issues with my virtual background. You will have to see my actual background instead. Okay, without further ado, let's start talking about C++ and Python. Let's start with that. I'm creating my own art now because we have AI, and we will talk about AI because we're talking about Python, and Python and AI love each other a lot as well, you know. But what you don't know maybe is that Python loves C++ inside AI modules. So we will get there soon. And I was already introduced. I always introduce myself, but I will just mention a couple of things. I have a LinkedIn channel that you can register. I post about C++, about Riddles. I'm teaching C++ there, so catch me there. I also have a new website that I'm maintaining where I talk about the same topics, but I can go deeper into them because, you know, that's a forum and not just a LinkedIn post. And I have started a CPP Next YouTube channel where I do videos about C++ and I go into deeper things. By any chance, anyone already seen my videos in, say, in YouTube? I guess not. So after the talk, not now, go watch a couple of the videos. Okay, let's start with a survey. I want to know how many people here actually use a different language when they're writing code. So here's our survey. Please answer. I will give another minute. Do we see results somewhere?
Yes, it should be on your screen as well. No?
For some reason, I don't see results.
Okay, hopefully if I once close, then it will come. Otherwise, I will just tell the stats.
Okay. I hope everyone voted, so let's continue. And again, I don't see the results, so can someone tell me what is the second most used language for you guys?
Python, 57%.
Python 57%. Yes, and I hope it's a landslide like everyone else, right?
Yeah.
It's more than everything else. Thank you. I'm sorry, I don't know. Again, Ubuntu. I don't know what to say. Okay, so another thing that I just want to mention, guys, this talk is interactive. I will ask questions, guys and girls. I will ask questions, and I want you to be interactive with me. Please answer me. And if you have any questions, don't hesitate to ask those questions. I will answer during the talk because I have a lot of slides to cover, a lot of things to talk to you about. And if we will go too far, it's going to be bad. So don't worry, just ask me questions. And I was really interested about this topic. Is Python the most used language for C++ developers? So I asked this question in my LinkedIn channel. And I had a good participation of around 500 people have answered. And as you can see, it's a landslide. So Python is used, 64% of people use Python and not other languages, not C. Basically, all the time they're telling you C, C++. No, it's C++ Python. That's the actual thing. And then I remembered, don't C++ core committee actually do these surveys? And yes, they do. And I remember that correctly. And as you can see here, 1,225 people answered. And again, C++ is the most used language for C++ developers. 72% of people use Python. Let it sink. Not C, not other languages, Python. So let's start with why C++? And I think it's a very ridiculous question for a C++ conference to be asked, right? We love C++, that's why we are here. And let's continue. Why Python? Why is Python used so much with C++ developers? And I think it's mostly these things that I'm going to illustrate here. It's fast development. So if you want to develop something new, developing it in C++ is kind of hard. Even for me, it's getting hard to do something that you want to do quickly. If you want to develop a new algorithm, it's horrible. I don't want to compile my code all the time. And that's where interpreted languages get in. I can use notebooks. I can separate it in a couple of parts. I can run one of the parts of the section in the notebook and it will always stay in the global state. Then I can run another one without running all the programming again and again. The debugging for algorithm is great. AI is wonderful because you need always to research your things. And it's really simple to write, right? Python is really simple to write. The interface is simple. Everything is simple. And that's why we use Python. With that, I want to tell you a couple of things about C++. So with time, modern C++ started to look more and more like Python. And I want to show you a couple of things that look almost exactly like Python now. For example, we have formatted strings. Who is familiar with that? Just answer with a thumbs up or something. Okay, great. I know. I see that people are familiar with that. Great, thank you. So this is really simple. If I want to print something out with Python, I can start a formatted string with saying f, and then I can print it with these curly brackets. Amazing, right? And it will print out a tuple as a tuple and the number as a number. I don't have to do anything. Simple. Then in C++, we got fmt lib. Who is familiar with fmt lib? Or std format? Oh, great, guys. You actually, who is using it? One. Okay. So as you can see, it's almost the same. We need to use fmt print. We're using curly brackets here to illustrate that we want to be an embedded string here, a formatted string here. And then we have a variadic argument list of a tuple and an integer, almost the same as in Python. The better thing in C++ is that those strings can be embedded during compilation. They cannot be printed during compilation, but they can be calculated during the compilation, which is great. And that's exactly what happens here, because everything is known in compile time. This string is actually formatted during compile time. And we get the same result. By the way, I didn't have to say anything. It knows how to format tuples, lists, anything you want from the standard. And it knows to format numbers. Isn't that great? Another thing, in Python, it's really easy to iterate over all elements of a collection. So we can go over all those elements and print them one by one. In C++, in C++11, of course, it's really simple to do that as well. And now it's even simple with ranges, but we will not go there because it's not about ranges here. It's about Python and C++. But I just wanted to illustrate it. So we are creating an array of 1 to 3. We are having out to I, and we are printing it with fmt. Almost the same. The code looks almost the same as Python. Another great thing is in Python, you can return tuples or multiple return types really easily, right? So here we have a function foo that returns 3 variables, the a, b that we receive into the function, and the calculation of a plus b. And then to get them in line 4, you can see a, b, c, and we are just unpacking or binding the values into a, b, and c. Then we can print those pretty easily. In C++, until C++ 23, sorry, until C++ 17, we couldn't do it exactly like that. We have to do it with std_tie. But look at this. We have a function. We are returning a tuple from the function. Basically, it's the same tuple that we return from Python. And then we're structurally binding A, B, and C in the spot of line 9. And we are binding those variables to be the answer from foo. And then we can print it. That's amazing, right? In Python, you could ignore variables that you want to be not binded with just an underscore. So here we have the same function and we want to be binded, but we only want one of the parameters to use only that. We don't care about anything else. So we know it's the third parameter. We can say underscore underscore C, and only C will be binded. In C++ until C++26, we had to use std_tie, and we have to use std_ignore. So std_ignore is almost the same as underscore. It's basically a type that can receive anything into it. It can be anything, and it does nothing with it. So it doesn't consume performance, but it's just a way to say, I don't care about it. And here we have the same thing. We have created C, and we are binding only C into the parameters that will be used after this line. With C++26, we got underscores. And it looks exactly the same as Python, except the square brackets. How cool is that, right? Almost Python. We're using it almost the same. And that's one of the reasons I'm saying C++ loves Python. The standard committee loves Python. And we are doing a lot of things to make your life easier, I hope. Sometimes we are making mistakes, but most of the times we are trying to make the life of programmers in C++ easier. And that's the results. And in my opinion, that's great that I can write those things in C++. If you go back to C++ 98, how horrific was that? But well, that's me. So if Python is that great and C++ is taking a lot of things from Python, why can't we just use Python? And the most important reason, the strongest point of Python is its own downfall. It's interpreted. And if it's interpreted, it's slow. And we cannot use slow languages when we want to do things. We are C++ programmers and we know that speed is important. Python is slow. And it's really easy to make mistakes in Python because it's a language that is dynamic. Everything might happen. And I want to illustrate a couple of mistakes that people make with Python and actually make their life horrible when they need to debug it. Don't forget that I'm going to show you things that are just little examples. But if you have a huge code base in Python, that's going to be hard to debug. So what's the problem in this function? We are just having a function that has an a as a parameter. We are adding a plus 1. Then we are using it in main with foo 10 plus 10. The problem is that we forgot return statement. And in Python, that's okay. It doesn't know. So you forgot to put a return statement. That it's not compiled. If it's not used somewhere in the main branch of your code, someone may use it and will want to add something to it, but it will not work. It will just return none, and none cannot be added to 10. Nothing can be added to 10 with none. So that's a problem. Here, will this code work? Please vote with thumbs up. Will this run? Who thinks it's gonna run with thumbs up? Oh, a lot of professionals in Python here. Yeah. So it's gonna run because Python is a global interpreted language. It has a global state. And because we defined B in line 5, it will remember it and it will bind the same B in the function because we use it before we call the function. How horrible is that? Think about it. If you made a small mistake in your code and you wanted to have two parameters, but you had just one parameter, and by mistake, you call the parameter inside the function the same thing that's already used in your code, it will be binded to that parameter. That shadowing is horrible. If you were in a compiled language, that wouldn't happen to you. Here we have another example. So here we have two functions. One is a, and one is foo that returns a plus b, and the other one is bar that uses a plus b. Someone expected to have like two lists. And in line 7 and 8, we're using it with foo. So if we use it with foo, everything is fine. But if we will use bar afterwards somewhere in the code, and again, if this code is not compiled and your bar usage is not placed somewhere where the code will be executed immediately, you will find that only when this function will be called the first time, and then you will get that you cannot add integers and lists. So in my opinion, sometimes using Python is great. Using Python is great, but those mistakes that we can make with this are pretty horrible. One of the less mistakes that I want to show is about what's important to us as C++ developers. So who knows what is this is? What is the representation of what is this? Who knows? Thumbs up? Okay, so that's max int for uint32. For us, as C++ developers, we know that if we add something to max int, to uint, it will wrap around. And if we will add something to max int, and this something in this case is 1, we would expect it to be 0. But in this case, because Python is a dynamic language, it doesn't care. So it says, oh, you're using max int for uint32? No problem. I will make it uint64 for you, and then we will just get this number plus 1. And that's not what we expect to be. Another thing for us as C++ developers, we want to get to low level. And in Python, it's pretty hard. So if you want to use something that is binary and you want to look at the bits of something, you have a binary built-in. But the binary built-in in Python is basically a string. So it's not as optimal as in C++, and we have to understand that, because if you are thinking that you will get something that is an actual binary, that will not happen in Python. Now that we understand that we have a lot of problems in Python, I just want to show you that newer versions of Python fix a couple of those, and how did they fix it. Here you can see that from Python 12, we got typing. We can actually use types in our functions. So you can see I'm defining the same foo function, but I'm telling Python, hey, I want A to be only integers, I want B to be only integers, and I want this function to return an integer, nothing else. And if we will use this function in the main, you can see we get a nice warning that says, you said that you want an integer, but it's a float, so that's ain't right. Please look at it. That's nice, right? That's getting there. Same thing now with the return statement. So if we don't have a return statement and we clearly stated that we want to return an integer, we will get a warning that says, hey, you said that you want to return an integer, but you're not returning anything. Please look at this. Please take notice. So this is nice as well. Another cool thing that we got in Python 12 is generic functions. So look at this. This is almost like C++ template functions. We are saying that foo is templated, or a generic function that uses t, which can be only integer or string. And then we're saying the function is receiving a parameter that it's list of t's, and another parameter that is a type of t, and we are returning a list of t's. Then we are taking a and appending b to it and returning it. So if we will use it as we are using it in line 8, everything is fine. We are providing a list of these integers and strings, and B is an integer. So everything is fine here, and we got exactly what we expected we will get. But if we will use something incorrect, we will get a nice warning again. Here it says T should be integer or string, but I got float. That ain't right. Something is wrong here. Please take notice. Another cool thing is that we can use like using in C++. So here you can see we are declaring a new type, which is a templated type or a generic type that can be list of these or a tuple of these. And we are using it in this function in line 6. And then we are using those in lines 10 and 11. Here, it's almost looked like C++. So Python taking some things from C++ as well. But as I mentioned, everything is a warning. If you will try and run the program, it will run, nothing will happen, and you get an incorrect result. You got a warning about something, you ignored it, and it runs. So what we can do with that? We have linters, and they are really important. We can use Flake 8 or MyPy. I prefer MyPy because it's more strict. And when we are using MyPy, and if we will try to do something like that, when we're saying that we want a type to be an integer or a string only, and a list of those types, and we are adding it, if we are providing a list of floats, it will show a warning here. But if we will run MyPy like this, we will get an actual error. So this is exactly what we want for Python. We want this to be almost as if it's a compiled language, and we can get it with those linters. The most important thing here is that, please, if you are using Python in your code base, I use Python in my code base a lot. We have CIs. We all have CIs. Please run linters before you're running your code. Let it fail. Fail during a linter, than to debug for hours and hours and hours. What about performance? So as Python gets newer, it gets faster. Look at Python 3.11. You can actually see that it's much, much faster than Python was before. That's pretty great. Python 3.12 became even faster than that because it has lazy imports and typing and all those things. I just couldn't find a nice graph to illustrate it, so we can see it for Python 3.11, but that's amazing that Python gets that fast. The important part in Python is not just that the language gets faster, we need to understand the internals of the language. So the language is so easy to write, and it can work with anything, but if you don't know the internals, you will get burned a lot. Here is an illustration of that example. We have two functions, function A and function B. They are doing the same thing. They're just summing the array that we have created in line 5. But one function is looping over the array, and the second function is using the built-in sum function from Python. Which one do you think will be faster? Who thinks that function 1 will be faster? Who thinks that function 2 will be faster? Thumbs up. Okay, and a lot of people are not sure. That's fine. So as you can see, we're running here for 100K times both of those functions, and this are the results. The Python function that loops runs for 266 seconds, and the sum function runs for 64 seconds. That's 4 times faster. How does Python do it? So because it's a built-in function, it uses C or C++. It has binding. Python has binding in it. And if you use the built-in function, you almost always will have better performance. That's not a great performance, but for Python, 4 times as fast, is much better. So you have to understand those things. Looping in Python, that's horrible. You need to understand that each time that you loop, the interpreter gets into a different state, and it needs to remember that state. It needs to understand if it has to loop or doesn't have to loop. It doesn't know when it ends. And so we are getting worse performance here. Now, we can get even better than this. We have a binded packages or modules in Python that we can use exactly for our needs. For this example, I want to illustrate NumPy. So if we will use NumPy, we will have 100K values, just as before. Instead of creating a Python array, or a list, sorry, we're creating a NumPy array of random integers. Of random numbers, not integers. This is not integers. And we are using it in function tree, just using the built-in function from NumPy for sum. We are getting the function and we are summing over it. And then we're running the same thing as we ran before, and we get 3 seconds. That's 21 times faster than before. How cool is that? So how NumPy does that? NumPy is an abstraction over continuous multidimensional arrays. It's binded to C or C++, it depending on the implementation. Older implementation used more C, newer implementation have more C++ in them. It creates a static array, not a dynamic one, and this array resides in C++ memory already, not in Python memory. So this binding makes it work much, much faster. Another thing that is important to remember, this array is not dynamic. You cannot keep multiple types in it. You defined it as C array, so you need to tell it which type of array you want it to be. In our example, it was floats. If you want it to be something else, we actually had to say, hey, we want this to be of type integer or of type something else. And all the values are the same. So because we know that all the values are the same, the array is static, NumPy can use SIMD, and it can make things run much, much faster than in pure Python. But it's important to understand the internal mechanics of our packages as well. This is Python. It's simple to write, but you need to still understand what you are doing as anything else, as any other programming language. Here we're trying to do the same thing, but instead of creating the NumPy array, we are creating a pure Python array of 50,000 values, a smaller one. We have 2 functions. One is using a built-in function, and the other one is using a NumPy function. And we are running them for 100K times, just as before. Now, please vote. Who thinks that function 2 will be faster? Please, with thumbs up. Who thinks that NumPy will be faster? Thumbs up. Oh, you're in for a surprise. The built-in function is much, much faster than the NumPy function in this case. Aren't you all shocked, right? We all expected it to be NumPy because it has all those wonderful SIMD and all C++ and C things and bindings and all the cool stuff. And it's much slower than pure Python function. Why is that? As I mentioned before, NumPy works with ND arrays. We have created a Python list. So the API is really nice because it's Python. It says in NumPy it's array-like, ND array-like. List it's ND array-like, but we cannot work with Python list inside C++ code. So we have to take all the values from the list and convert them to ND array, to push them to C++ memory, then to convert them back into a list and return the list back to us. That's a huge overhead. That's why it's so slow. So you have to understand when you're using something that you have to understand how things work to not get those pitfalls. And what are the takeaways from this? Always use models that are already defined. You don't need to implement everything by yourself. And if you want performant Python, you can get it. You just need to know what to use and how to use it correctly. If you are using an open source model for optimization and binding, always understand the API. Always know the little things, because if you will not do it correctly, it will bite you. It will bite you hard, as you've seen before. Now, I mentioned AI, and I love AI. I love working with it. We are not working with it in speed data, but for me, it's like my side projects. I always try to do things with Python and to try to train new models to get things that I want. And one of the best modules in C++ or frameworks in C++ to do AI is PyTorch. PyTorch is basically an abstraction of a continuous multidimensional arrays. Sounds really familiar, right? It has abstraction over AI models as well. It's an easy way to do matrix multiplication and build new AI models. The core implementation is in C++ and CUDA. It's a really, really easy way to write CUDA programs from Python without understanding exactly how CUDA works, but to get the results from your GPU. It's an easy way to train your models. So here's an example of PyTorch. We are creating random array and then just a regular array. We are reshaping it to be a huge matrix. Look at the size of those matrices. And then we are timing it for 1,000 times. It's going to be slow. Look at the size of the matrices. So it's only 1,000 times, not 100K times as before. And how easy it is in Python to multiply matrices, just using a regular multiplication. Without you knowing this regular multiplication, bind it to C++ code or CUDA code. Amazing, right? And in my opinion, that's pretty good results for a huge matrices to be multiplied in Python for 40 seconds, for 1,000 times multiplications, 1,000 multiplication for 40 seconds. That's pretty amazing. But we can get better results. As I mentioned, we can use CUDA for our advantage. And it's pretty simple. Just look at it. We're saying we want to use a CUDA device. I have ran this code on my PC. My PC uses 480 Ti, an NVIDIA card, which is not an industrial car, but you can see the results soon. We're saying, please, we want to use a CUDA device. We are creating the same arrays, but instead of creating those arrays on CPU, we are creating them directly on the device. And then we are using the same thing. We are multiplying 1,000 times the matrices, one after another. And this is the result. 0.04 seconds. Because GPUs are so good with matrix multiplication, we are just killing it here. And because everything stays on a GPU, on the device itself, we don't have overheads here. But if we are using something incorrectly, as I'm doing here, we are doing almost the same thing. But here I'm creating a round trip. Each multiplication is copied back to the CPU. And I'm running 100 times here because it's that slow. That's a magnitude lower. We get 31 seconds. Because the overhead is so great of copying the data back and forth from GPU to CPU, we get worst results. So as always, if you are using a package, you need to understand how to use this thing correctly. Here, I just wanted to illustrate how easy it is to create a neural network in Python, in PyTorch. Here, I'm creating a neural network from everything that I have in PyTorch. And this neural network is just to create something that takes mNIST images and tries to find out which one is a shoe. Just a network, but that's fine. And it's pretty amazing how easy you can do those things in PyTorch. I have a link for one of my notebooks in Colab. So after the talk, you can go and look at those things. And as we've seen, Python has a lot of things to offer you performance. And if you want to write just in Python, you can actually do it. You can do it and you can get performance if you know what you're doing. But sometimes the open source modules don't have everything. And sometimes we need to do the work for ourselves. So we need to write our own bindings. How do we do that? Let's look at this function. For some unexplained reason, I have this function in my C++ base code, and I need to test this function in Python because I have some researchers that need exactly the same function, and they cannot implement it in Python because we need exactly the same code to run. That's silly, but just for example. The good news are Python is written in C, and it's actually called CPython. So CPython is our core interpreter that provides the Python interpreter to you. Actually, when you're running Python, you're running a C program that interprets your code, keeps a state of a Py object and a global object, and you run everything. What's great about it is that it looks kind of like this. So we have a script, we have a Python core that we are using. Inside the core, we have an interpreter. The script is running inside the interpreter and creates a Py object, and we are communicating with that Py object. We have input and output devices. So you don't think that you are running in something that is a C program, but it actually is. And because it's a C program, it allows us to have extensions. So basically, if you want to extend it with your own binded project or extension, you can do it. It provides a python.h file that exposes all Python API to you. And to use it is pretty simple. We will see it in the next slides. But if we use it and we create an external or an extension object, we can actually use it inside the interpreter and communicate with the Py objects that we have already created. How cool is that, right? You can create it by yourself, and your external code that is written in C or C++ is actually used inside Python interpreter. So how do we do that? As I mentioned, we have python.h. That's pretty simple. We have to include it, right? Everyone knows that we have to include something in C++ or in C. Then we have to write a C function. That's pretty self-explanatory, I think. But then we have to create the Python version of the function. The Python version of the function needs to get self because we have a state, and it has to have the arguments. Everything is Py object. Everything is managed as Py object. We need to create the integers that are the parameters. Then we have to parse the parameters, and we have to tell the Python interpreter, hey, those two parameters will be integers. Please parse them into A and B. And then we have to call the actual C function with A and B. Then we can return a Python object from the C++ flow that we have created. After that, we need to define the function in Python. So here we're actually defining it and saying, okay, this function is foo. It will be called pyfoo. It will use pyfoo function. It will have met var args, and it will do something like that. It's just a documentation, and we need to keep a sentinel. So everything is written here in C. Just for an example, I will not write C after this example. Don't worry, we are using C++. That's not enough. After that, you have to define the module. So we are saying we need to define a module. This module needs to initiate. This module name will be foo module. This module will use foo methods. That's not enough. We have to define an init function. So when you're importing a model, CPython is calling an actual init function. And this init function in C needs to look something like that. So here we are saying, okay, if you are importing us, we need to create the model called foo model. That's not the end of it. Then you have to create a setup py file to install it. And you have to say, okay, this model is an extension. So please create an extension from foo-model.c that we have created. And then when you have the setup, we need to say this extension model is a model. I don't know about you, but for me, I'm lazy. I don't want to do all those things each time that I'm using something that I want to bind in Python. And just note that all this work was for one lazy little function. Think to yourself how much work you have to do if you have huge models that you have to bind. That's not maintainable. That's pretty hard to do. And it's if you have a project that uses a big build system, that's not maintainable as well. So if you're lazy, you will love this part. I'm lazy. We will talk about 3 kinds of binding. We will talk about static binding, dynamic binding, and a language that's called CPython. Cython. Cython is pretty cool because it's a language that looks almost like Python, but you can do and bind everything to C++ really quickly. CppIndiaCon is the coolest thing that I'm going to show you here, but you have to bear with me until the end. And the simple modules are PyBind11 and Boost Python. So these modules are the base of our talk. If we are using PyBind11, it's pretty easy right now. We just need to include PyBind11h to our code. We have to implement the C++ function the same as it was before. And then we have to say PyBind11 module. As easy as that. We have a macro. Macros are evil, but what you're going to do? Here they are important. You are using this macro. It will create all the bindings for you. Then you are saying this model documentation is X, and then you're defining a function. Look how easy is this here. You just need to define it. You're saying what function it is, and you're saying which arguments you want to provide to the function. Everything is done for you behind the scenes. Then in your CMake, because we want it to be part of our huge code base, in CMake you have to find the package PyBind11. Let's say, like me, you are using Conan package manager. And Conan developers are pretty funny because if you will look at line 10, you will see when I need to link something, I'm linking it with PyBind11. All do not use. I don't know. They have some twisted kind of humor, and this is actually in their documentation to use that. In any case, that's as easy as that. You are creating a module just like you're creating it in C++, and then you're linking PyBind11 to it. That's all it takes. We still need to create a setup function, but here the setup function doesn't need to extend anything because we're creating it already as a model. So it's pretty easy as that. And we can actually do it from our CMake code as well because we have install. So we're saying during the installation, please execute a process. This process is a Python executable, and this Python executable will run setup.py and do an installation. So you don't need to do anything manually. When you install your module, everything is done for you with CMake, right? As easy as that. That's maintainable. That's how you need to work with Python and C++. I just want to give you a short illustration of Boost. So Boost and PyBind11 are almost the same. Just if I'm not mistaken, Boost was before PyBind11. You still need to create the C++ function. You still use a macro that binds the code for you. You're defining the function. And that's it. Very simple. The CMake will look a little bit different because now we are looking for Boost and a Python 3 component. We need to find the interpreter and the Python libraries. We are linking it to Boost Python 3, and that's it. Afterwards, everything is the same. You can do the same things. Then you can ask, then you probably ask yourself, everything I show until now, it's C code. It's not actually C++ code. What about classes? So here we have a simple C++ class, struct, with two functions, foo and bar. To bind them with C++, with PyBind 11, it's pretty simple as well. We're creating the module as we created it before. Then we are using an instruction from PyBind that's called class. And we are telling it you are actually templated on a CPP class. So it knows to create this Python class for you. Then you are defining the functions and you're saying, okay, I need a default constructor for this class, so I'm exposing it. And I'm defining my two functions that I will use, foo and bar. They are receiving the arguments for the function pointers, so Python will be able to call those function pointers afterwards. You're probably asking yourself, what about performance? So right, we're writing everything in C or C++. It must be running much faster than Python. And no. Pure C++ runs in 4.2 milliseconds. Pure Python code runs in 1 second, 1.2 seconds. CPython code runs in 1.1 second. I think it's just noise. So let's say that Python and CPython runs the same. And PyBind 11 runs in 5.7 seconds, the worst one of them all. I don't have Boost here, but Boost runs a little bit closer to CPython, but still, it's a little bit slower. So why does it happen? We have to remember that we are using Python and C++ in the same time. So the variables or the parameters are written in Python. When we use them in Python, they need to be transferred back and forth from Python memory to C++ memory, from Python type to C++ type. We are copying them back and forth, and then we are outputting them out. Another problem, PyBind 11 had a weird decision to do everything as smart pointers and a lot of allocations. So it makes it really, really slow. You have to understand that maybe performance is not exactly what you need. You just need to bind those things together. But you have to understand if you're using PyBind, you will pay with an overhead. And another thing that we have to remember, just like with CUDA, we need to use hot spots or hot code with Python. So if you want to do something in C++, you don't transfer one little argument and then do it back and forth. You need to provide a huge chunk and then work on the chunk in C++ and just then transfer it to Python. You will still have an overhead, but if your calculation is much longer than the IOs, you will still get better performance than pure Python. We can fix that, as I mentioned, with hotspots areas. PyBind 11 and Boost has special types that are already binded to Python and C++. For example, we can use directly PyDict in C++ code. So we don't need to provide a back and forth communication between those two. So if we will use that, we will have already a binded object that has both of the codes already, both of the environments already available for us. Both Boost and Python have ND arrays built into them. Basically, they are binding NumPy. And in PyBind 11, it's called array_t. So we can use array_t not to copy all the values around. Important thing to remember that Python is a garbage collected language. So if you will return a pointer from your function, it may be dangled because Python can clean it for you, but you want to use it in C++. So when you use Python, you always need to use smart pointers for those not to be eliminated. That's the important parts if you want to use bindings from these libraries. Now, this is an example of how PyBind11 works with ND array. So we have C++ code that not just using a regular array, it's using an ND array. We are summing everything up just as before. And here in this case, C++ got a little bit slower, a little bit. And PyBind11 got much faster. So it's almost running a CPython. You understand, if you're using this type, you don't have the overheads because everything is already binded to Python. So it's always important to know what you're using and bind things correctly. Cython. So sometimes it's not enough to go from Python to C++. Sorry, from C++ to Python. Sometimes we also want to go from Python to C++. We want to run C++ functions from Python. I mean, Python functions from C++. And Cython is exactly our answer. It's a rich language. It's an actual language that lets you bind Python code to C++ and Python code to C++ as well. We can do inter-op communication between two languages. Sometimes you want it. I personally use it. So C++ to Python looks something like that. We have a class inside a namespace that have virtual functions, and then we have a class that inherits from the pure virtual class that implements those things. To create it, we have to write a pxd file. Pxd file is just the Cython version of an H file. Here we do all the declarations. Here we are saying, I want to use libc++. Cython actually binded all libc++, almost everything from libc++ to Python. So we can import from memory a shell pointer because we want to use a shell pointer in our code. Here we are saying cdef extern from cclass.hpp. That's how I called my HPP file with the class. And we are saying we're going to use namespace important, the namespace from the file. Cython knows how to look at to the file and see everything from the namespace. Then we have to use cdef cpp class. Cpp class means that it's a pure C++ class. We will call it C abstract, and we are telling Cython, please use the class from C++ that name is abstract. So Cython knows to go into that class and parse it into what we expect here. We're saying it will use abstract with expect. We're saying that we want to throw exceptions from this function that might happen. That's okay in C++. And then we're defining foo and bar. Afterwards, we're defining another C++ class, the real class. The real class is just inheriting from C abstract, just like in C++. And we are saying that we will implement those functions there. Then we need to create a Python function, a Python class, something that we can use from Python itself. So we're using cdef class. When we are using cdef class, we're saying, okay, this class I want to use in Python. It's not a pure C++ class. We are calling it pyreal. And we have a member inside it that we are defining and saying cdef, this is a C definition. And this member is a share pointer. That means this share pointer will always reside in C++ memory. Afterwards, we need to create a pyyx file. Pyyx file is the equivalent of Cython to CPP files. So here we are doing again, we are C importing everything from our module. We are using a make share and null pointer from memory. And we are using a special operator from Python, from Cython that's called dereference. Basically, dereference is a way for you to use asterisk, like in C++. In Python, asterisk means something else. So we need to use dereference to do that. And here we are implementing the pyreal class itself. We're using cinit. Cinit will be called before init in the class, and it will init everything that is needed for the C++ memory. And here we are doing it almost the same as in C++. We are using make shared. I wanted to use serial, an actual C++ type, and create serial from it. And this will reside in Python and in C++ memory, and I can access it. And the foo function that we implemented is basically using int A and int B, as we expected. Look at the syntax, it's really similar to C++. Then we are dereferencing the get function from the shared pointer. The get function from the shared pointer is basically returning a pointer to serial. We are dereferencing it and using foo function from the C++ class itself. That's it, as easy as that. Then we have to Cythonize it. Cythonizing it is pretty simple. It's just saying, okay, we want to use Python 3. We want to use C++ and not C. And please do it on this PYX model. Afterwards, we can create a CMake file that does the work for us. We are creating a custom command. This custom command will work on the PXD and the PyYX files. The output from that command will be a CPP file that will be generated by Python. And the command is the same command that I showed you before. Then we are adding a library. This library is a shared library that will use my model CPP. Because you're saying that it will use my model CPP, when this target will be built, it will call the custom command before the target is starting to be built. That's nice. We need to set target properties not to use lib, because Python really likes to call modules exactly as the libraries in C++. So if it's a foo module, it should be foo-module.so. It prepares the init function exactly as the library name, without prefixes. So we can do it easily in CMake. And then we have the Python install function that I already showed you before. So this is maintainable and you can do both ways. If you want to do a call, if you want to call a Python function from C++, for example, if you want to work on JSONs, we have JSON libraries in C++, but for some reason you don't have access to it, you can write something really simple like that in your Python code. cdef public means this function will be exported to C++. We are providing a string as a path. We are using JSON from Python. We are loading it. We are manipulating it, and we are returning the string back. Inside your C++ code, you will have to work a little bit harder because you will have to load the Python interpreter into C++. That's what we are doing with the DL open here. We are loading the Python interpreter. And then we are initializing everything. We are starting the threads can start running from here. We are importing my module, and then we can actually use it in C++. As simple as that. Few words about exception that we need to understand. Python cannot throw exception into C++. So if your Python code threw an exception, C++ will do nothing with it. If you want to throw exception into C++, it's really easy to do it in Python as well. So you need to create a function in C++ that's called throw C++ runtime error. And this function can be defined inside your Python code. And each time you are throwing something inside Python or Python, you need to call this function. This way, it will be propagated to C++, and you will get a pure exception in C++ and not just a crash, which is much worse. And now we're getting to the best part here. Dynamic binding. So CppYY is the new module in town. It's pretty amazing. CppYY uses runtime C++ binding. It's doing it because it uses Cling. Cling is a C++ interpreter that is based on Clang. So you can write your code and it interprets C++ on the spot exactly as Python. Look at this. All the hoops that we had to jump before to bind the function to Python, we can do like this now. We can say CppYY, cppdef. We are writing the C++ function that we want to bind. Then we are using GBL, it's just the global namespace from CppYY, and we are using foo. That's it. That's actually from my terminal. Amazing. And the performance is amazing as well. Because it's using Cling, Cling is very optimized. So pure C++ runs in 4.2 milliseconds. And cling, or CppYY, that binds things during runtime, runs faster than boost CPython or Cython. How amazing is that? More things, you don't need to install anything. You don't need to duplicate STL because it's actually using STL as a C++ file. It has full support for templates, full support for inheritance, and you can even use Python callbacks in C++. I will show you the examples. When I started using it, I was amazed how magnificent this thing is. Here we have our very interesting example that I showed you before. We have the abstract class, but in this example, bar, we return an array, and we have the real class that just implements it. Nothing fancy here. And then we want to use it inside Python. So we are importing CppYY, and this is basically the code that I had to write. That's it. Import CppYY. CppYY include features h, just the same as C++. We're including a file that we wrote that's called features.h. Then we are importing from the global namespace in CppYY the real class. We can see that real class is in GBL. Then we are initializing it. We are creating a C++ class in Python, and then we are using the member function. Again, almost no code, no hoops that we had to jump. Everything just works. To implement bar, we needed to use array. As I mentioned, we don't need to do anything with STL. STL is already built into CppYY because CppYY just includes the files from C++. We are using the array header file, the same array header file that we used in the C++ file. We are creating a class that's called PyReal that is inheriting from the abstract class from C++. Then we are creating the functions that we want to use, foo, that are doing something, and bar, that is using array of int and 10. This is a template class that we are instantiated inside Python and using it directly from C++. How amazing is that? To use it, you just need to instantiate it and then to use the function. And you got exactly what you wanted. I mentioned that cling is just Clang. So Clang is really good with dealing with templates, right? So here we have a template called callIt that has a type name, that has template parameters R, variadic arguments U, and variadic arguments R. We are saying that this function receives a pointer to a function that returns R and receive all parameters with U. And then we have the arguments for the function. All we have to do inside the function is use invoke with the function pointer, and we are providing the arguments into the function. And look at this. Inside Cython, I just imported callIt because it's inside features. I had to import features.h. Then I had to do callIt, import callIt from the global namespace. Then I'm creating a pure Python function that's called f. We are saying f is receiving an a that is an integer, b that is an integer, and we are returning a float. Then we are writing the code that we need to do with it. And then we're just calling callIt from C++ with a Python callback. During this callIt event, cling takes the template, instantiates it for us, and creates an actual function from the templated code. And this templated function instance can actually be called with Python callbacks. And we get what we wanted. Again, we are getting 40, exactly as we wanted. One thing that we have to note, I had to provide integers and floats. Basically, I had to tell Cling, I have those types for it to actually understand what we are trying to instantiate. And that's exactly the magic of Cling and CppYY. So closing notes. Use the right tools for what you need. Don't implement everything by yourself. Be lazy. Lazy is good when you're a programmer. Try to Cythonize your code, a pure Python code. If you Cythonize it, you can get performance out of it. If you have to write something by yourself, understand the tools that you are using. Avoid downgrading pointers. Be aware of the threading problem in Python. Sadly, I don't have time to talk about the threading problem in Python. And we are done. Hopefully you enjoyed it. And if you have questions, please do ask them.